Welcome to another Mathologer video. Okay, to begin, thank you very much Jesko Mathis and Aaron Prince for your very funny comments on my sun-deprived complexion. Basically Nosferatu, right? It's these comments that inspired this brand new Mathologer t-shirt that you all will be looking at for the rest of this video. Like it? Okay, so you've all been tortured with what's next questions since primary school, right? 1, 2, 4, 8, 16, what comes next? Well, of course, the answer is 32, right? Well, not necessarily, since the pattern doesn't have to be doubling. It could be something totally different. Have a look at this. Put equally spaced dots around a circle. First just one dot, then two, then 3, 4, 5, and so on. Now, connect these dots in all possible ways. There. And let's count the number of regions that materialize. For the first circle there is just one region. Next there are 2 regions, 4, 8 and 16. And now what comes next? Well, just count and you'll find that the next number of regions is 30 and not 32. Surprised? Well, maybe not. At least some of you will already have seen this cute, devilishly misleading pattern previously. It's an absolute classic and an absolute must-know for anybody interested in maths. What this shows is that when it comes to answering what's next questions, you should never jump to conclusions. Anyway, if the rule is doubling, then we know exactly where we're going, and we can really kill this question by saying that the general formula for the nth term of this sequence is 2 to the power of n. If, on the other hand, the rule is number of circle regions, then the killing formula is surprisingly complicated and was actually only found in 1997 by the mathematicians Björn Poonen and Michael Rubinstein. This killing formula looks like this. Ooh, scary. If you're interested in the details, check out the description of this video. For hundreds of years, another seemingly very simple what's next question has provided mathematical megastars like Euler and Ramanujan with many a sleepless night and led to some of the absolute highlights of their mathematical careers. That insomnia-inducing question and some of those highlights are the subject of today's video. Well, that was pretty, right? But what actually happened? Well, what you just witnessed was an animation of the 8 different ways of writing 4 as a sum of positive integers. So there they are again. Very nice. Now, how many different ways are there to partition an arbitrary positive integer like this? Obviously not enough information to venture a guess, right? So let's list the different partitions for small numbers and see whether a pattern jumps out at us. There, that's the partitions for the small numbers. Okay, let's count. Obviously, there's only one way to express the number 1. For 2, there are 2 ways, just 2 and 1 plus 1. Okay. For 3, there are 4 ways. And as we've already seen, there are exactly 8 ways to partition the number 4. Okay, 1, 2, 4, 8. So obviously the next one is 16, right? Or am I trying to trick you? Well, let me show you a very ingenious way to answer this question once and for all. At the bottom, there are 4 blocks which represent the number 4 that we're chopping up. Notice that there are 3 gaps between those 4 blocks. There. Let me show you what happens when we open and close these gaps in various ways. Can you see it? Of course you can. The different ways of splitting up the integer 4 corresponds to the different ways of opening and closing those 3 gaps. But how many ways are there of doing that? Well, each gap is either open or closed, so 2 possibilities for each gap, and there are 3 gaps, which gives a total of 2 times 2 times 2 is 2 to the power of 3, is equal to 8 different ways. So I didn't trick you. Unless I tricked you by making you think I was tricking you. Looks were not deceiving. 1, 2, 4, 8, and what's next? Well, in this case, 2 times 2 times 2 times 2 is equal to 16, then 32, and so on. For a general integer n, there is 2 to the power of n minus 1 ways of partitioning it. Easy and super pretty, right? Now, did you enjoy this warm-up exercise? Well then, you're ready for the real deal. Okay, time for the killer question. Look again at the lists of partitions over there. Did it bother you that there's a lot of repetition in those lists? There, 2 plus 1 and 1 plus 2, they're basically the same, right? And if we don't count these two partitions as different, then the number 3 has only 3 different partitions. What about the partitions of 4? Okay, get rid of the repetitions there, and instead of 8 partitions, we end up with only 5 really different partitions of the number 4. There. So, how to think about this refined list of partitions? Well, as you'll see, it's not that easy. But quick and dirty, you can think of the collection of all truly different partitions as some sort of super duper self-similar fractally thing. Something like the Mandelbrot set for numbers. Well, okay, a bit clickbaity, but anyway, can you see it? Even a superficial look at sets of partitions reveals some patterns that repeat over and over. And that's just the obvious tip of an absolutely immense iceberg of complex patterns. This structure has many important surprising connections to other parts of mathematics, computer science and physics. But for now, let's focus on capturing the hidden patterns in the numbers of these partitions. Okay, let's go. 1, 2, 3 and 5 partitions. What's next? Any guesses? You can probably think of at least a couple of easy patterns that fit so far. But it's definitely not enough information for an educated guess. So let's throw in a couple more numbers. What's next? Well, there are 7 ways to partition 5. The plot thickens. Still got your guess ready? Well, let's throw in the next number. And it is 11. Aha! Can you see it now? Well, 2, 3, 5, 7, 11 are all prime numbers. And that one at the beginning is sort of an honorary prime. So what's the next prime number? Well, 13, of course. Well, that wasn't so hard, was it? Well, not so fast. I hate to break the news to you, but actually the next number is 15. Damn. Okay, so there goes our prime numbers conjecture. So what is going on here? What if we add in more of the sequence? Anything now? Yeah, no. Okay, time to send out the bat signal. There he is, Batman or Superman or Madsman, whatever. All mythologers will recognize the guy with the towel hat. Leonhard Euler, one of the megastars of maths. He was the first to really investigate partitions and these partition numbers up there. And Euler discovered some truly amazing patterns in the sequence of partition numbers. Want to see some of Euler's genius again? Well, of course you do. Okay, so let's go. At first, when only these 4 numbers were visible, did you perhaps think of another sequence? 1, 2, 3, 5? That's also the start of that other super famous sequence, the Fibonacci sequence, right? 1 plus 2 is 3, 2 plus 3 is 5. Now, let me ask you a weird question. That 1 in front, that's the partition number for 1, right? Now, if your life depended on assigning a partition number to 0, what partition number would you assign to it? Make a choice now. What did you decide on? My bet is that you chose either 0 or 1. Let's go for 1, which is also the official choice and makes for an even longer Fibonacci start to our partition number sequence. Okay, let's intone the Fibonacci mantra. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8, but we want 7. Well, we are off by 1, but we can save things by subtracting the very first one on the left. 5 plus 3 is 8, minus 1 is 7. So what I'm saying is that maybe to get the next number in the sequence, you always have to add the last number and the second last number, just like with Fibonacci, but then you also have to always subtract the fifth large number. Okay, let's test this theory. 7 plus 5, that's 12, minus 1 is 11. Works. Next. 11 plus 7 is 18, minus 2 is 16, and not 15. Damn again. Well, I was not lost yet. Let's just adjust our rule one more time and also minus the 1 at the beginning. There, now it works. 11 plus 7 minus 2 minus 1, that's 15. Next. 15 plus 11, 26, minus 3, 23, minus 1 is 22, works. 22 plus 15, that's 37, minus 5, that's 32, minus 2, that's 30, magic. Okay, the next. 30, 22, 7, yeah, that's 42, works again. We definitely seem to be on to something. And next. Yes, works again. Is that it? Is that the real rule? What do you think? Sorry, but no. Okay, 56 plus 42 minus 15 minus 7 is 76, one short. But by now you can probably guess how we're going to fix things, right? We simply add the 1 in front. And then what? Well, most likely we just keep shifting until we encounter another mismatch, chuck in another plus or minus to adjust at the end, and repeat. And believe it or not, this crazy scheme actually turns out to be exactly what happens. Overall, you have to keep adding pluses and minuses forever. Also, it's always 2 pluses, followed by 2 minuses, followed by 2 pluses, and so on. Well, that's great. But for this pattern to actually be useful, for example, for calculating a partition number we don't know yet, based on the ones preceding it, we have to know in advance how exactly those pluses and minuses are positioned. So let's continue our pattern hunt. Okay, so to calculate a partition number, we add the first last number, then the second last number, then we minus the fifth last number, okay, then we minus the 7th last number, then we add the 12th last number, and so on. Okay, so we end up with this sequence of position numbers for the pluses and minuses that we have to, what's next? Well, when is this pattern hunt going to end? Soon, promise. Anyway, here are the first couple of position numbers. At first glance, the sequence of numbers looks just as mysterious as the one we started with. However, after staring at this sequence for a minute or 2 or 3, many people will notice something remarkable. Actually, maybe give this a go. Stop the video at this point and try to spot the pattern. I'll wait. Want a hint? Yes? Well, ponder the differences between consecutive numbers. What are those differences? Well, the difference between 2 and 1 is 1. Okay. Here the difference is 3. Okay. 7 minus 5, that's 2. And so on. Can you see the pattern? No? No problem. Let me give you another hint. That's a big hint. You can all see the pattern now, right? There in the orange, 1, 2, 3, 4, 5. Whoever has trouble with this pattern should change channels now. And in the green, 3, 5, 7, 9, and so on. That's the odd numbers. How super nice is that? But also how super bizarre. How come these two intertwined primary school patterns make an appearance here? Well, we'll get to that. Anyway, using these two interleaved patterns, it's now easy to extend this sequence of position numbers forever. For example, the difference between the next position number and 70 is 7. And so the next position number is 70 plus 7 is equal to 77. And what's next after that? Well, the next green odd number is 15. And so the next number in the sequence is 77 plus 15, which is 92. Patterns within patterns within patterns. How amazing is all this? And we have not even started drilling into the why. To summarize, here's how we can build a partition number sequence thanks to the genius of my all-time favorite mathematician, Leonhard Euler. Make up a row of squares that continues forever to the right. We'll write the partition numbers onto these squares. We put in the first one straight away. Then we make up a second row of squares that extends forever to the left. There. That row of squares we label with the pluses and minuses. Then we line up things at the ends like this. And then we calculate one partition number after the other based on the ones that we've already calculated. So the next one is plus 1, so it's 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. And 5 plus 3 is 8 minus 1 is 7. And so on. There. It's like a machine, right? Calculating these numbers. So, challenge for the coding experts among you. Based only on what we've discovered so far, compute the 666 partition number. Leave your answers in the comments. As I already mentioned, the theory of partitions has many important and surprising connections in and outside mathematics. Just as an example, here's a very unexpected maths connection which is established by slightly tweaking Euler's incredible partition number machine up there. Let me explain. The tweaked machine works exactly like the original, except that the first red entry up there increases by 1 every time we move the bottom row of squares. Have a look. Okay, line up again. Now, plus 1 as usual. Now this thing actually goes up like a counter, okay? 2 plus 1 is 3. Okay, counter goes up again, doesn't really matter, but 1 plus 3 is 4. Okay, 3 plus 4 is 7. Okay, 4 plus 7 minus 5 is 6. And so on. Have a look at the sequence this produces. 1, 3, 4, 7. Now it plummets down to 6, then 12, then down to 8 again, and so on. This sequence jumps around like crazy, really insane. But believe it or not, there is a beautiful pattern hiding there. And the pattern is this. Take the value of the counter, in this case it's 12, and list all its factors. 1, 2, 3, 4, 6, and 12. That's all the factors of 12. Now add up these factors. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 6 is 16, plus 12 is 28. There, 28 in the output of the machine at this point. And that always works. The sequence up there is the sequence of the factor sums of the integers. How absolutely mind-bogglingly crazy is that? Why should writing a number as a sum of integers have anything to do with the sum of its factors? Marvelous. Also, just think about it. Which numbers are special in terms of having the least number of factors? The least number of factors. Yep, the primes. A prime number p has only 2 factors, the number itself and 1. Can you tell where I'm going with this? Well, what this means is that we can use this modified machine as a prime detector. We can use it to check whether a number is prime. How? Well, just work the machine until the counter shows the number we're interested in. Then our number is prime if the output of the machine at this point is 1 greater than our number. Here's an example. Let's play dumb and pretend we don't know whether or not 7 is prime. So spool back to when the counter was showing 7. Well, the output is 8, so 1 greater than the counter, and so 7 is a prime. How about that? Work the machine. Okay, 8 in the counter is not prime because the output 15 is more than 1 greater than 8. Now it's not prime because of the same reason, not prime, but 11 is prime because the output is 12, 1 greater. Now isn't this a magic machine? Even Euler himself couldn't believe his eyes when he first discovered this wonderful connection between prime numbers and partitions. Just imagine being the first person to discover something as amazing as this. Can you imagine the aha moment? Today I'll be busy disassembling Euler's original machine for you and sadly won't have the time to also delve into the guts of this modified machine. But as usual, for the super keen among you, I've included some links in the description where you can further explore this connection and some of the other things I'll only mention in passing. Okay, so we saw that it's easy to calculate the position numbers of the pluses and minuses using the simple orange-green pattern. And of course, Euler would have spotted that pattern straight away. Even more so, as a real maths pro, he would have recognized that this position number sequence is just the sequence of the so-called pentagonal numbers. Let me explain. Pentagonal numbers. Well, you may not realize it, but you already know the triangular numbers and the square numbers. Here are the first couple of triangular numbers. So the triangular numbers are just the numbers of dots in the different equilateral triangle arrays. In fact, we've already encountered these numbers in many other methodology videos. These numbers are just the different 1 plus 2 plus 3 plus etc. sums. For example, the triangular number 15 is just the sum 1 plus 2 plus 3 plus 4 plus 5, right? Just last video we had it. So let's quickly again figure out the formula for the nth triangular number, the number of dots in the triangular array with side n. So the nth triangular number is just n times n plus 1 divided by 2. All regular methodologists will probably already have committed this formula to memory. Comes up all the time, as I said. Triangular numbers? Tick. What about square numbers? Well, pretty obvious. 1, 4, 9, 16 and so on. Finally, pentagonal numbers. Now, quickly, let's also derive the formula for the nth pentagonal number. We're really on a roll today. Now, why are we doing this? Well, because that's what we're doing here in Mathologer. We do real maths, which means we prove things. Okay, that's the formula for the pentagonal numbers. Spectacular, isn't it? But wait, who forgot why we're interested in these numbers? Confess, you don't remember? because they are supposed to be the key to the position numbers for the pluses and minuses. And sure enough, there they are. Amazing, right? What do pentagons have to do with partitions? Apart from both words starting with P. And why do we get only half the numbers? What about the other half? Ready for another surprise? Well, the other numbers is what you get when you plug in the negative integers into the formula. Okay, let's check. Plug in -1. Autopilot. Okay, shuffle, 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 shuffle. 4 divided by 2. Yep, that's the 2 that fills the first gap between the pentagonal numbers. Now plugging in -2, we get 7. Yeah, you can check that, and so on. Fantastic. Challenge for the keen among you. Use this formula to prove that the sequence of differences really always follows the simple pattern that we discovered earlier. As usual, write up your proofs in the comment. And the really easy fun challenge, calculate the 36th triangular number. Oh, and for later, I'll call the pink numbers the pentagonal numbers and the blue ones the other pentagonal numbers. So how are you enjoying this topic so far? In the rest of the video, I'll explain why Euler's partition number machine works, why the pentagonal numbers are the key to this mystery, etc. For this, we'll actually have to look into the nature of the partitions themselves. But before I dive into the guts of things, let me quickly tell you a little bit about what came after Euler's discoveries. I've mentioned Ramanujan at the very beginning. Where does he enter the picture? Well, as we've seen, there is a nice pentagonal formula for the position numbers of the pluses and minuses. So what about a nice formula for the partition numbers themselves up there? Well, that turns out to be a real killer. And that it is a killer is really not that surprising, right? Basically, to get the growth rule for the partition numbers, we started with the simple growth rule for the Fibonacci numbers. They are Fibonacci numbers. And then we refined this Fibonacci growth rule infinitely often. I already derived the formula for the nth Fibonacci number for you in previous videos, and it looks like this. Plug in 0, it spits out the first Fibonacci number 1. Plug in 1, it spits out the second one, then the 2, and so on. That's already pretty complicated and amazing. Now imagine infinitely more complicated and infinitely more amazing, and you get the formula for the partition numbers. Well, actually, you don't have to imagine anything. Let me just show you what this formula looks like. Ooh. Again, plug in 0, it spits out 1, plug in 1, it spits out 1, then 2, and so on. But of course, this is a totally insane formula. It's not even clear at all how you would go about evaluating it. Also, it's swarming with pi's, e's, i's, infinity, hyperbolic functions, a derivative, and so on. And this formula is due to Ramanujan. Well, not quite. He had the basic idea and then developed it together with Hardy while he was living in England. The finishing touches were applied by the mathematician Rademacher 20 years later. I won't have the time to say much about this amazing formula in this video, hopefully another time, but at least I'd like to give you a glimpse of the incredible power of this formula by showing you what even a really tiny part of it can do. To get to this tiny part, throw away everything except for this. Not much left, right? Now, differentiate and express the hyperbolic functions that pop up in terms of exponential functions. Don't worry about the big words, okay? And you get this. Throw away the last 3 small terms and you're left with this. The minus 1 over 24 doesn't do much either, so let's throw that away too. And so eventually you get this. All right. After all this throwing away and simplifying, what's left is this very famous approximation of the partition number function that is still amazingly accurate. Let me show you just how good this approximation is. Okay, on top is the actual function that spits out the partition numbers. And at the bottom is Ramanujan's approximation. And actually, come to think of it, since the partition numbers grow in a way that is a refinement of the Fibonacci growth process, our Fibonacci formula should also give a fairly good approximation to Pn, right? Okay, well, let's first compare red with blue. Not a bad fit, but see what happens when we zoom out. Things really appear almost indistinguishable at this magnification. Just to put things into perspective, to see just how good Ramanujan's simple formula captures our partition monster, I'll now add the Fibonacci approximation. There. There, huge difference. Just for emphasis, here at n is equal to 26, Fibonacci is already 80 times as large as the partition function. So while Fibonacci is really way off very quickly, Ramanujan tracks incredibly well forever and ever. Really nice, but also really tricky to prove. But if you think that this formula is the final word on the partition function, what's next? Think again. Even today we still discover many new incredible things about this sequence of numbers, and since the plan is to keep making these videos until I'm 100 years old, I'm pretty sure I'll talk about some of these remarkable discoveries in future videos. Now for the why. To understand why those pentagonal numbers make an appearance, we really have to have a look at integer partitions. In fact, let's have a look at integer partitions in a very visual way in terms of dots. Okay, here again is our house-shaped deformed array of dots for the pentagonal number 35. Let's deform this array of dots further like this. Then we can interpret this array as a graphical representation of a special partition of 35. There, 9 dots in the first row, 8 in the second, and so on. 35 is 9 plus 8 plus 7 plus 6 plus 5. Not bad, huh? Very pretty. In general, we can represent any of the partitions we are counting in this video in this way. Since the order of the summons doesn't matter, we'll always order the corresponding rows of dots from largest to smallest, going from top to bottom. These dot diagrams of partitions are usually called Farrer's diagrams, named after the mathematician Norman Farrers. That's him, Norman Farrers, who, apart from being a mathematician, was also one of the vice-chancellors of Cambridge University. Here are a couple of other examples of Farrer's diagrams. It may already have occurred to you that there is a second way to interpret a Farrer's diagram as a partition if we consider it made up of columns instead of rows. Right? There are 9 dots in the first column, 6 in the second, and so on, which gives us a second partition of 35. Very interesting, isn't it? So there is this hidden connection between different partitions of a number established by these diagrams. In fact, there are lots and lots of other beautiful relationships hiding in partitions of integers. Finding and exploiting these hidden relationships leads to deep insights about partitions and their applications in maths and elsewhere. I'll now show you one such hidden relationship which was discovered by Euler and which is the key to our recursion formula for the partition numbers. This relationship is called Euler's pentagonal number theorem. So pentagonal number, finally. So in what follows, we'll focus on the default interpretation of Farrer's diagrams in terms of rows. So at least for the rest of this video, forget about the second interpretation in terms of columns. Okay, I'll call a partition even if it contains an even number of summons. And I call it odd if it contains an odd number of summons. The example over there contains 9 summons, and so it is odd. The pentagonal number theorem focuses on the distinct partitions, those partitions of a number that consist of distinct summons. In other words, the pentagonal number theorem is about Farrer's diagrams, all of whose rows are of different lengths. The example over there is not distinct because the 5s and the 1s repeat, right? Okay, let me show you an example without repetitions, a distinct one. There, the summons of this partition are all different, and of course the pentagonal partition we started with is also of this type. Okay, now, Euler proved that in general the number of even distinct partitions of an integer is equal to the number of odd distinct partitions. Again, in general, the number of even distinct partitions of an integer is equal to the number of odd distinct partitions. But there are exceptions to this rule. And those exceptions occur exactly when the integer we are partitioning is pentagonal. Let's have a closer look how this pans out for the smallest integers. Okay, we are focusing on the partitions without repeated summons. So let's throw away all the partitions with repeated summons, which is actually most of them, all gone. Okay, now highlight the odd partitions in red and the even ones in green. There. I said that in most cases there will be the same number of odd distinct partitions as there are even distinct partitions. And even in this short list, half the cases are of this type. There. The same number of odd as even partitions. Let's throw these away and focus on the exceptions. Supposedly, these exceptions should be pentagonal numbers, and they are. So let's extend this list of exceptions a bit. There. And this really works out. The numbers of odd and evens are different for all our pentagonal numbers. And how exactly these differences pan out also meshes in with the pluses and minuses that go with the pentagonal numbers. Remember those pluses and minuses? If there is one more red than green, there's a plus. And if there's one more green than red, there's a minus. Another way of expressing this is to say that for every integer, the difference between the number of odd and even distinct partitions is 0, right? So if they're the same, then the difference is 0, obviously. Unless the integer is one of the pentagonal numbers, in which case the difference is 1 if the pentagonal number comes with a plus, and -1 if it comes with a minus. Okay, but now for the why. Well, there's a really beautiful visual proof of Euler's pentagonal theorem that the American mathematician Fabian Franklin published in 1881. It's been called the first serious piece of mathematics that came out of America, by some very snobbish European mathematician, of course. Here's one of our distinct partitions. There are two features we'll focus on. First, the bottom row. Then there is the diagonal. The diagonal starts in the upper right corner, and then it continues at 45 degrees until we run out of dots in a line. So in this case, the diagonal is just 2 dots long and the bottom is 3 dots long. Here are 2 more examples. In the second example, the bottom is shorter than the diagonal, and in the third example, they are of equal lengths. Now we'll transform these partitions according to the following ingenious rule. If the diagonal is shorter than the bottom, as in the top diagram, then we make the diagonal the new bottom like this. If the diagonal is not shorter, like in the other 2 examples, then we make the bottom into the new diagonal like this. Three observations. First, we only move dots, so before and after we're dealing with partitions of the same number. Second, the transformation always either adds 1 row or removes 1 row, so it turns even partitions into odd partitions and vice versa. Third, before and after we're dealing with distinct partitions. Okay, now let's apply the transformation to the new partitions. Notice that in the bottom example, the diagonal and the bottom have a dot in common. But it's fine, the rule still applies. Now let's transform. What was the rule again? If the diagonal is shorter, we move the diagonal. Well, the diagonal is now shorter in the second and third examples. Here we go. In the top example, the diagonal is not shorter than the bottom, and so we move the bottom. Can you see what happened? No? Well, we're back where we started from. So starting with any distinct partition, applying the transformation twice gets us back to the partition we started with. This means the transformation splits the distinct partitions of a certain number into pairs. Every pair consists of 1 even partition on the left and 1 odd partition on the right. And these 2 partitions are swapped by the transformation. And the existence of such a pairing implies that if there are no exceptions, which is the case for most integers, then there are exactly as many odd distinct partitions as there are even ones. And this is exactly what we wanted to show. Now there happen to be 2 types of exceptions. Where would you expect those exceptions to be lurking? Well, there was this case where the diagonal and the bottom had a point in common, remember? If you think about it for a second, that's really the only case where something can go wrong. Actually, if, as in this example, there's a big difference between the lengths of the bottom and the diagonal, having a point in common is actually not a problem. But now let's shrink this difference in lengths and see what happens. Okay, so as we've seen, this works, no problem. There, no problem. What about this? The diagonal is still shorter, so it still moves. Still no problem. Shorten the bottom 1 more time. Okay. At this point, the diagonal is just 1 shorter than the bottom. Anyway, it's still shorter, so it moves. Aha, there's the problem. The resulting partition has a doubled up row at the bottom and so is no longer distinct. This is the first type of exception. Shorten the bottom 1 more time. Now the diagonal and bottom are equally long. Since the diagonal is no longer shorter, the bottom moves. Ooh, that doesn't work at all. So the bottom and the diagonal being of equal length is the second type of exception. In fact, In terms of exceptions, the two types we've just encountered are all there is. Shorten things further and things start working again. And nice, the second type of exception are just the pentagonal partitions. And now it would be great if those other exceptions corresponded to those pentagonal numbers of the second type. And they do. Let's have a look. To get the second type of exception, we start with a pentagonal diagram and then extend it by doubling up the diagonals like this. Right? This is going the other way as we did before. And yes, it works. There, 2 points, 7 points, okay. 15. Great. Now I'll leave it as an easy exercise for the keen among you to show that the number of dots in these special Ferrous diagrams are just these other pentagonal numbers. And this completes the proof of the pentagonal number theorem. Super pretty, don't you think? Again, for numbers that are not pentagonal, there are no exceptions to the pairing, and so there are an equal amount of odd and even distinct partitions. For any pentagonal number, there's one exception to the pairing, the pentagonal partition up there. And so the difference between the amount of odd and even distinct partitions is 1 or -1, depending on whether the exception is odd or even. Okay, at this point you're probably all pretty exhausted, eyes are glazing over, brains are about to explode, and you are just happy to take my word for it that Euler's pentagonal number theorem now somehow translates into Euler's machine, that amazing recursion formula. But for the super keen among you, let me at least quickly sketch how we get there by focusing on one particular instance of the recursion formula. If you really want to proceed, maybe now is a good time to steel yourself by taking a bit of a break, grabbing a cup of coffee, and then rejoin me for the final dash up the serious mathematical mountain that we're scaling today. Or, if you've seen enough for now, skip straight to the end for another incredible What's Next puzzle. Okay, so you really want to find out about the last piece of the puzzle. Very good, I'm proud of you. So let's focus on this instance of the recursion formula up there. In symbols, the numbers that actually do something here are these. There, P1, the first partition number, P6, the sixth partition number, and so on. And these numbers are supposedly connected like this. P13 is equal to P12 plus P11, minus, plus. Okay. So how does this identity follow from the pentagonal number theorem? Ready for our final mathematical magic trick for today? Okay, P13, this is about partitioning 13. So let's take 13 dots. Split those 13 dots into two groups of any size. For example, a group of size 6 and one of size 7. 6 plus 7 is 13. Pick an arbitrary partition of 6, say 2 plus 2 plus 1 plus 1. Doesn't have to be distinct, any partition whatsoever. There, 2 plus 2 plus 1 plus 1. And pick a distinct partition of 7, say 4 plus 2 plus 1. There, that one on the right is distinct. Now, focus on the bottom rows. Now, we'll do some more ingenious transforming of diagrams. In particular, we'll move one of the bottom rows to the respective other side. Can you guess which bottom row will move in this example? Right or left? What we want at the end of the move is another arbitrary one on the left and another distinct one on the right. So which one moves? Well, pretty obvious. The rule is, if the bottom row on the left is shorter, it moves, otherwise the bottom row on the right moves. In this example, the bottom row on the left is not shorter, so the one on the right moves. And yes, at the end of the transformation, we are again facing an arbitrary partition on the left and a distinct one on the right. Plus, the parity of the one on the right will have changed. And unleashing the transformation on the new pair will get us back to the starting pair. Should all be a bit familiar, right? Now, this new transformation pairs up our pairs into super pairs. Like that, right? What's super nice about this super pairing is that there are no exceptions. And this means that there are exactly as many pairs with an odd distinct partition as they are pairs with an even distinct partition. Always. Very interesting, isn't it? But how are we going to use this fact? Well, just follow our nose. How many pairs are there with an odd distinct part? Well, for the split into 6 dots on the left and 7 dots on the right that we've been focusing on so far, there are P6 arbitrary partitions on the left to choose from, and the number of possible odd distinct partitions of 7 on the right is, well, let's call it 07. And so there are a total of P6 times 07 pairs with 6 on the left and 7 on the right. Now we can also split our 13 dots into 5 and 8 dots, which gives this many extra pairs with an odd distinct partition. So to get the number we are really after, the number of all pairs with an odd distinct partition, we simply split 13 in all possible ways and then add up the corresponding products. And then the existence of our super pairing of pairs says that this number is equal to the corresponding number of pairs with an even distinct partition. Ooh. Well, anyway, don't be scared. In a moment, most of what you see over there will vanish into thin air. Anyway, subtract everything on the right from the stuff on the left. There. And this is where it all comes together. Can you see it? Well, maybe pause the video again for a moment. Okay. Well, Euler's pentagonal number theorem tells us that the differences in the blue brackets are usually equal to 0, except if we're dealing with one of those pentagonal exceptions. Right, at the top 13 is not a pentagonal number, and so O13 minus E13, the difference between the numbers of odd distinct partitions and even distinct partitions of 13, is 0. And the same is true for all those other non-pentagonal numbers. There. This means that all the highlighted summands are 0. Vanish into thin air. And now the pentagonal number theorem also tells us that all those remaining differences in the blue brackets are all either equal to 1 or minus 1. Looks very promising, doesn't it? So let's keep charging ahead. The bottom row is a bit special. O0. Well, obviously, with 0 being an even number, there are no odd distinct partitions of 0, and so O0 is 0. On the other hand, E0 is 1, counting that one way to have nothing on the distinct side and all 13 points on the arbitrary side. Okay, the rest of the differences follow the pattern that we established earlier, 2 plus 1s followed by 2 minus 1s, etc. as far as it goes. Ta-da! And that's it. We just proved that Euler's machine really does calculate P13 correctly. Well, that was quite a bit of work just for checking P13. But of course, the argument that I showed you is completely general and also shows that Euler's machine does the right thing for all the infinitely many partition numbers, not just P13. The power and magic of maths. Wonderful, isn't it? Well, that last dash up the summit was quite something, wasn't it? Just in case you couldn't quite keep up with the insane pace, I'd say just give it another go at half speed and really take it one step at a time. Absolutely worth it. I hope you enjoyed this mathematical tour de force. As usual, let me know what worked and what didn't work for you in the comments, and ask for clarification if you did not understand something. Anyway, that's it for me for today. Except, as promised, here's another super nice what comes next problem for you to puzzle over. It will be interesting how many of you figure this one out and whether anybody will be able to justify their guess. What? You're still here? Amazing! Okay, might as well show you something else that I find really pretty. Ready? So as we've seen, the partition numbers 1, 2, 5, 7, 12 and so on are just the numbers of dots in these special Ferrous diagrams there. Focusing on the shape of these diagrams, it's also really easy to see where the bizarre pattern in the differences between adjacent partition numbers comes from. Remember that yellow-green pattern? There. That intertwining of the orange 1, 2, 3, 4, 5 and so on, and the green odd numbers 3, 5, 7. Here's how you can see at a glance, actually 2 glances, where this intertwined pattern comes from. First, the differences between these pairs are 1, 2, 3, 4, and so on. Really obvious that this will continue forever when you look at it this way. Nice, huh? Second, the difference between these pairs are 3, 5, 7, 9 dots and so on. Also super pretty and super obvious why we get the odd numbers here, isn't it? If you'd like to tell me that you really made it all the way to here, please just leave the comment, I made it to the very end. And this is really it for today. Until next time.